Hello, everyone, and welcome to First Saturday Science monthly live stream event. We're so excited to be here with you today. My name is Alyssia.
My name is Dakota.
And my name's Tavia.
I want to take a quick second to welcome our new little scientists coming in today. We're so excited to have you today, and if you're returning, welcome back. This month is the month of December, and the weather outside is frightful. I'm just kidding. I'll keep my day job. Don't worry. This month, on a serious note, this month is December, and we're covering thermodynamics. And you might ask, Alicia, what is thermodynamics? Well, thermodynamics is the process of how heat, um, it's the process of how heat moves from one area to another area. And actually, heat happens to be energy. So when we're talking about thermodynamics, what we're actually learning about is how energy is moving throughout a system. Today's experiment, we'll be talking about an endothermic reaction. And an endothermic reaction means that something is absorbing heat and it will be cold to touch. So that's what our experiment is going to be today. And Tavia, our little scientist, is going to give you a little bit more information. And I do want to point out in some of our materials on our Facebook page, we did say to have warm water, but this experiment actually works better with room temp. So just throwing that out there. All right, I'm going to let Antavia and our little scientist Dakota take it away.
Hi, everybody, and again, thank you for joining us again. We're very excited to learn with you. So for December, as Alyssia mentioned, we're studying thermodynamics. And a little bit of background for thermodynamics is that, as Alyssia mentioned, it's the study of energy transfer and the physics of the way energy moves throughout the universe. And so what we say is that with a closed system, you cannot create or destroy energy. And so it's simply transferred from one system to another. So a good example is that when you take food, when you eat food, those plants have taken energy from the sun, and they've utilized all of that beautiful, warm sun energy that keeps all life active on Earth today. And they transfer that energy into sugars for them to use. And then when you eat that, you're becoming part of that energy chain. And all kinds of things go on in your body to produce ATP and energy in your body. And then you can then use that energy in your body to do things that also create an energetic reaction. And so can I shake your hand? If I shake Koda's hand, I'm using the energy that I ate for breakfast this morning, and I'm transferring it into my hands, into motion energy. And Koda is doing the same thing. And so all of that energy is being put out into the universe once we activate that energy. And so for today's experiment, we're doing a thermochemical experiment. So what is thermochemistry? Thermochemistry is the study of the energy and heat and of a chemical reaction and a physical transformation sometimes look similar. And when we talk about them, it's important to remember that physical transformations are when a state of matter changes into another state, but chemically it's still the same product. So a good example of a physical change or transformation is the melting of an ice cube. So when an ice cube melts, it turns into
Water.
It turns into water, exactly. And similarly, if you put water in a pot and add a bunch of heat on your stove, what happens to that water, Koda?
It gets hot.
It gets hot, and then it boils, and then steam vapor rises away from that water. And that water isn't chemically different. Those water molecules aren't different. They've just changed their state, their physical state. Whereas with a chemical change, those are not necessarily reversible processes. So when the chemical change occurs, you can't necessarily push them back into what the products that you had before. Whereas,
Technically, you could freeze the water.
yep, you could freeze with a physical change, you could refreeze the water and change it back to its another state. An interesting point about a physical reaction is that you're always able to separate its constituent parts, right? So if you mix sand and water, you'll have watery sand. But at the end of the day, if you tried really, really hard, you could get all of the sand out of that water and you would still have water and sand. Whereas with a chemical reaction, for example, burning of wood, if you burn a log, you're creating a plasma and you're eventually creating some smoke. And that log doesn't necessarily exist in the same form, and a chemical change is occurring. You're producing a lot of heat work. That's what keeps you nice and toasty in front of a campfire. And you can't necessarily reverse that. You can't really get all of that smoke and all that stuff and all the heat that you took. You can't push that back and create another log. And so that's an example of a chemical change. And so thermochemistry likes to look at these energy changes, right? The transfer of energy from one system to another in the chemical reactions, particularly on a system's energy exchange with its surroundings. And so that kind of brings us to the lesson about endothermic and exothermic reactions. And Alyssia had mentioned that endothermic reactions feel cold to our bodies. They feel cold to touch because they're absorbing heat from its surroundings. That reaction that's taking place, it needs more energy than it has. And so it's going to start grabbing heat energy from its surroundings because it wants more. It needs more to happen. And so remembering that, the opposite is an exothermic reaction. So what would you guess happens in an exothermic reaction?
It's harder than an endothermic reaction.
Yep, the heat. Yep, it's hot. It feels hot. And so an exothermic reaction is one that is going to release heat, like the burning of wood during the campfire. Its reaction is so excited. It's got so much energy. It's pent up, kind of like when you have so much energy in your body and you're just not tired and you just want to run around. It's kind of like that. So it just like gives off all of this wonderful warm energy, which can sometimes be dangerous if your chemical reaction is volatile. But typically, if it's just kind of hot to the touch, you can still kind of feel its warmth without touching it too. And so that's an example of an exothermic reaction. And so in the reaction we're going to do today, it's an endothermic reaction. And when in our materials that we gave you guys, we mentioned using warm water, as Alyssia had mentioned. So in order to feel the endothermic reaction, we found after doing some test trials ourselves, we found that using warmer water actually overcompensated, and we weren't able to feel that endothermic reaction. So that's the reasoning. That's the logic behind our kind of pedaling backwards and saying you should actually try to use room temperature water if you're able to. And then another quick note before we go into our experiment is this is going to be kind of a messy eruption. And so it's important that you have your reaction vessel, like a cup or a small bowl or something, inside of a larger vessel. That can be a cookie sheet, a casserole dish. Today we're going to be using a big bowl to kind of hold all of our reaction, to keep it a little bit tidy, just so that it doesn't go everywhere. And if you find that you don't have something that would work, you could always use a kitchen sink or a bathtub if you need to, just something to hold on to it. And so now we're gonna go into our reaction, right? If you're ready. Are you ready, Fana?
Yeah.
Are you excited?
Yeah.
Yeah. Okay. Oh, and then one last thing, safety, right? So what do we do in lab to keep safe?
Put goggles on and have coats.
Put goggles on. So Dakota's gonna put on some goggles, and we wear lab coats. Lab coats should cover your limbs in your body. And then we always wear closed-toed shoes in lab as well. You don't want any of your skin exposed except for maybe your hands. And then also a quick note that everything in this lab today is safe to touch. We're using baking soda, which is in a lot of baked goods, like muffins and cakes. And then we're also using citric acid, which is naturally found in fruits like lemons and oranges. What else? Can you think of something else with citric acid?
Apples.
Apples, yep, apples have citric acid in them. And then we're also utilizing hand soap and water. And so those are definitely things that are safe to touch. And then I have long hair, so I'm going to put it back just so that my hair doesn't get in the way. Oops, I'm sorry. Which is always important. And now we're going to start our experiment, if you're ready.
Hello, welcome back. I'm Alyssia. I'm going to take us the camera and switch it over to the experiment really quickly. So you're going to be able to see kind of a really quick tour of one of our laboratories here at the College of Science building, or the Science Education Center. All right, let's get started. And I'm going to take us down to the experiment.
Okay, so now we're going to have Dakota start the experiment. Now, the first thing we always do in lab when we're starting an experiment is analyze our procedure. We're always going to look at the procedure, and this is going to come in every First Saturday Science take-home kit. Hi again to STEP Academy students who are joining us today. Everyone in the STEP Academy class that we've sponsored this month is going to get all of these supplies. And if you are an educator or you work with children and you're interested in partnering with us in some capacity, or if you're in the Twin Cities area and you're interested in the science kits that we provide, please reach out to us. We'll keep our promotional contacts in our literature, so feel free to reach out to us. So we're going to open up the experimental procedure. Wonderful. Oh, that's perfect. It's kind of like a little book. And the first thing is materials. You always want to check your materials. We've got a bottle of soap, check. Half of a cup of baking soda, check. 3/4 cup of citric acid, check. Measuring cup, check. Mixing stick, check. And the materials that are not included in your kit but that need to be prepared are warm, we said warm water, room temperature water, check. For one experiment, you'll need 3/4 of a cup. To use up the whole bottle of soap and all the rest of the ingredients that we included, you need about 3 cups of water total. But for this first portion, you only need 3/4 of a cup. And so the other item is a large mixing bowl or wall pan or tray, as we've previously discussed. And so step 1, put the cup from your kit into the large bowl or tray pan. Perfect. And now, step 2, mix about 1/4 of the soap with about 1/4 of the warm water from the mixing stick. Mixed with the mixing stick. So we have about 8 ounces bottles, and so 1/4 of 8 ounces is 2 ounces. So we're gonna open this bottle. You're gonna twist. Yep, perfect. We don't really need the pump. And then you're gonna pour about 2 ounces of soap. So if you can see, the 2 ounce line is right there, so we're going to pour about that much soap in. It doesn't have to be exact, but try to be about right. That. Oh, yeah, you know. That's good. All right, so we've got about 2 ounces of soap, give or take. And we'll put it back into the bowl. And then, yeah, it's a little bit blurry. Our camera is a little bit blurry, so I wonder if maybe we just need to.
Mm-hmm.
Oh,
yep,
perfect.
exactly.
Okay. Sorry about that, guys. Let's try to think it once. There we go. Perfect. Okay, we fixed it. And now we're going to add about 3/4 of a cup of water. And I've got a measuring cup to make it extra easy. Yeah, you can just fill that cup right up. Perfect. Try to push it a little bit forward so you can see. And then pour that right into the cup. And then we're going to mix it with our stirring stick. It's okay. Just to fully mix up that soap and that water. And then the next step says add about 1/4 of the baking soda powder. And so 1/4 of the baking soda powder is going to be about 1/8 of a cup. So I'm going to put the baking soda powder here. And we have a 1/4 cup measurement. We don't have 1/8 of a cup. So I'm just going to fill this up about halfway, give or take. And then we're going to toss that in there. And then you can mix it up with this stick. Okay, now we have readied our reaction. This addition of the citric acid, which is our next step, is where the eruption is going to start. So get prepared, make sure you're ready, and it's going to be about the same amount of citric acid as baking soda, maybe just a little bit more. So get ready, hold it over, and then get your stirring stick ready because it's going to start right away. And the more you stir, the crazier the bubbles are going to be, which we love over here. So go ahead, toss it right in there, go for it. Then you're going to mix it. Go for it. And keep mixing. Keep going. And you can see it oozing out, and it's completely safe to touch. And I encourage you to touch it. Please give yourself that sensory experience. It's so cold. Dakota, why don't you feel it? How's it feel?
Oh.
It's freezing. Even though the water we used, it wasn't hot or anything, but it was room temperature. It wasn't cold. But this reaction.
Hey everyone, I'm gonna touch too. Yes, it is freezing.
It's very cold. So this is kind of our Sudsy Snow experiment. We really wanted to do this one because we wanted to show you what that energy transfer feels like. And remember, an endothermic reaction means that this reaction needed way more energy to occur than it had within it. And so it took all this, it's taking all that heat from your body, from your hand, from the universe, in order to overcome that activation energy to have that experiment continue. And this is an example of an acid-base reaction. And the byproduct is CO2 gas. And so you might have joined us earlier in the semester when we talked about greenhouse gases and carbon dioxide, and how carbon dioxide is a greenhouse gas. Carbon dioxide is also something that plants like to take in order to in order to grow, and then they put oxygen for us to breathe. And so what's happening here is you can kind of see it shrinking, right? It's getting smaller as the reaction pushes forward. Well, now I just agitated it. But over time, it will shrink, and you'll end up with not that much stuff, even though we almost filled the bowl. Because the byproduct was a gas, and the gas is trying to escape from that soap and that water, and it's trying to move outwards. And so what we end up with is a bunch of fluffy foam, but really the majority of this volume is actually just gas. And so once that gas finally escapes, once it's able to leave, we're not left with a bunch of stuff anymore. And then also another fun part is once this reaction is complete, I encourage you to put what's left into a spray bottle or a jar, because this is actually a wonderful all-purpose house cleaner. This is wonderful for cleaning your stove or cleaning up any paint messes you might have at home. And so this is a wonderful way to have fun in the kitchen with some science, and also not waste any products if you have the means to do so. Oh, yes. I'm going to grab a paper towel because our hands are all wet. I'll be right back.
I know, it's super cool, right? And if you hear this mysterious voice that just appeared, it is I, Alyssia. Hello.
Okay, and now as a special surprise, we're going to do one more reaction. So we kind of discussed, we're going to dump out the bowl, put it, because we're going to use the bowl again.
Okay.
Just use that one.
Surprise! Did you guys know that we were going to do another activity? What? First Saturday Science, what are we doing? Again, if you hear this mysterious voice that just popped out of nowhere, it is I, your friendly First Saturday Science coordinator, Alyssia. Right now, Antavia is getting our second activity, our surprise activity, ready to go for you. So make sure to keep watching. Also, make sure to subscribe, and we're bringing you our surprise.
Okay, so for this second experiment, it's just 2 ingredients, and this is really just because we wanted to show you what a physical transformation looks like. So the experiment that we just did was a chemical transformation. We took a couple different ingredients, we mixed them together, they reacted together, and then they created a gas byproduct. So you can't necessarily shove that gas back into the products and get the same ingredients that we started with. Whereas with a physical transformation, you're not necessarily making anything new. You're just moving things around, and you're utilizing kinetic energy and kinetic movement in order to have a reaction, but you're ending with the exact same ingredients that you started with.
Question, what materials are you using for this surprise activity?
So what we see in this Erlenmeyer flask, this is a Diet Cola. And then Dakota is going to show you, what are they, Dakota?
Mentos.
And where might you find them?
Let's just show them a little bit better. Yes.
These are available in your corner store and your grocery store. These are actually chewable mints, so you're totally safe to eat them too. Although after the experiment, you might not want to. So what we're going to do is we're going to take just 4 of these Mentos, and very quickly, Koda's just going to drop them all into the Erlenmeyer. Maybe 2. Yeah, let's do 2 more. Agitate it a little bit and get those Mentos going. And so you can see the production of bubbles. It actually didn't erupt as much as we like. So I'm going to pour. So this is actually, okay, so this didn't go through quite as well. This is a really good example of remembering that you have to prepare for an experiment, right? So what would have normally happened is it would have rushed out. But I think what happened is we let the cola sit out too long because we prepared the experiment ahead of time. And so I think the carbon dioxide gas probably didn't get they actually got a really good opportunity to escape. So this is a good example of preparing properly. But what would have happened is it would have rushed out really fast. It would have erupted, kind of like a volcano. And what would have occurred was a physical transformation because the carbon dioxide gas is actually already in the soda. When you drink a bubbly drink, it has all these yummy effervescent bubbles that that's kind of what makes you burp when you drink a carbonated beverage. That's all carbon dioxide gas that's pushed into like fizzy water, exactly. It's all pushed into the water. And so when you drop the Mentos in, the Mentos have like a really rough texture on the outside, and there's little pockets where the carbon dioxide is able to interact with itself and then self-propel out of the soda. And so carbon dioxide is released, there's lots of foam, it's like a big eruption, it looks really cool. But at the end of the day, you still have soda, you still have water, you still have sugar, and you still have CO2 gas. Nothing chemically is being altered at all. And so it looks really similar, but the transformations are actually very different.
All right, round of applause. This is what happens when you're live, everyone. I'm going to flip our camera back up so that we can say our outro. You're going to see our wonderful lab yet again. You're going to see our wonderful little scientists in Antavia. And me. Hi, I'm back. I want to say thank you for watching our live stream event. I would like to make a special note that we will not be streaming in the month of January because we will be on winter break. But I would like to know everyone's favorite part of the experiment. What was your favorite part of the experiment?
I like challenges. I like being kept on my toes. So my favorite part of the experiment was actually realizing that the Mentos and Coke experiment wouldn't work if the Coke was out too long. It makes sense. It made me think about why it didn't work, and I had to use my logical thinking and problem solving to think about maybe why that didn't work. So that was my personal favorite part.
Dakota, what was your favorite part?
My favorite part was seeing the chemical reaction of the soap, the water, and the baking soda and citrus acid.
Good job. I would say that my favorite part, I would say that my favorite part of the entire experiment is the fact that solution is clean and safe and that parents or teachers can use it in your classrooms or in your house. And it essentially is almost a zero waste experiment. That's my favorite part. And I hope everyone enjoyed. And I'm glad that you're here. And I hope you come back and expect for our virtual workshop to be out at 2 p.m. in your emails. Thank you.
Bye.